again. All right, so this first slide after the homework from yesterday is just kind of a revamp of yesterday's discussion over the relationship between critical value, level of confidence for confidence interval, and the alpha level for a hypothesis test. So we looked at a two-tailed test yesterday. In a two-tailed test, if we let, I'm just going to make up some numbers. If we let's say 0.025 or 2.5% of the area be in the lower tail and 2.5% be in the upper tail, and that would be an alpha level total of 0.025 plus 0.025, which is 0.05, then that would correspond to constructing a 95% confidence interval. So we could do the alpha level 5% hypothesis test, pair it up with the 95% confidence interval, and they should be in agreement on how we treat the null hypothesis, whether we have evidence for it or against it. Okay, the one-sided is a little bit different because in a one-sided, all of your alpha is on one end. So if we did a hypothesis test with an alpha level of 5%, and it's a lower tailed test, and if you did an upper tailed test, you just flip this over into the mirror image of it. So it's the same picture, just flipped. If all of the 5% is in that lower tail, and there's a confidence interval that gets paired with it, and this one's kind of a weird one. If you got 5% in the lower tail, the mirror image of it is a 5% in the upper tail, even though that's not reject region. But between those two, you would have, I put that on the wrong side. Did you notice that? I can't do the mirror image sitting down, evidently. If I did the mirror image of that line, then what percentage is actually between those two cut scores? 90. So a one-tailed test would require a little bit of adjustment. If we did a one-tailed test, bless you, and we let our alpha level be 5%, which is pretty standard, and we wanted to pair it up with a confidence interval that has the same level has the rejection at the same place, then we would actually have to do a 90% confidence interval to get an equivalent or same decision about what's going on with our population. Okay, so just a thought about how those pictures look. In a two-tailed test, we split that alpha equally between the two ends. So each end technically has half the alpha in it. You can't see it because it's just too dark. There's an alpha divided by 2 in that dark space, but I don't know that you can see it at all. But it'll be okay. So that's just to kind of do cleanup on that idea that we built yesterday. So now on to new stuff, the actual error discussion. So next slide. Hypothesis testing is not exact. Statistics is not exact. Statistics is about taking what we do know and using it to predict what we don't know. Or at least that's the big chunk of statistics that's left that we're studying now. So one or two things has to be true. You start a hypothesis test, the first thing you do is write a null hypothesis. And that null hypothesis makes a claim that's either true or false. Either the new medicine is better or it's not better. So when we say the new medicine is the same as the old medicine, it's either true or false. There's nothing in between. There's no probability that it's true, probability that it's false. It is true or false. It's either right or wrong. Either the percentage of kids who are homeless has gone down, or it's the same as it was before. So that one's black and white. The problem is we don't know what the answer is. We don't know whether it's true or false. If we knew whether it was true or false, we wouldn't do hypothesis testing. We would just already know. And hypothesis testing is about trying to get at the truth that we can't really get our hands on. So the null is true or false. Got to get that in your head. There's no probability attached to that at all. So because we don't know whether it's true or false, we run a test and we collect a sample to see if the sample supports that claim or does not support the claim. And we use that sample to make a decision. So you run the whole test and then you either reject the null or you don't reject the null. And that decision might be right and that decision might be wrong. We may have a true null hypothesis and fail to reject it and do well. We may have a true null hypothesis and reject it, and that's bad. That's a type 1 error. We may have a false null, claim it's correct, and have a wrong answer, a wrong decision there, and have a type 2 error. So there's always a possibility that our decision will be wrong. And the ugly thing is we never know if it is, because we never knew the truth to start with. We still aren't going to know the truth when we're done. So there are 2 potential types of errors, and you have to be able to discuss those errors in context on the AP exam. So what's helpful, I think, but you might not need to draw it for yourself, but I think it's helpful to look at it, is what I call the decision-making box. And we saw a prelude of this box yesterday in the reading. So there's 2 things going on, and I want to make sure I don't use the same version. Okay, so over on let's do a 2x2 box. And you can pretend it's beautiful and straight and right angled, and you can make yours prettier. On the left hand side, I'm going to put the truth. The truth. What is the truth about the null? Well, either H naught could be true, so we'll put that in the first row, or H naught could be false, and we'll put that in the second row. So only 2 things possible with a null. It's true or it's false. One of each. Doesn't matter which one's in which row, as long as we just put them somewhere. And then in the other direction, we have our decision. So the decision we make at the end of the test. And we could say that H naught is okay, and so we fail, well, I guess I should write that there, fail to reject H naught. We fail to reject H naught. I should have started with the words fail to reject. Or we could reject the null. We can say, oh, there's not any evidence that's substantial, so we're going to retain the null. Or, oh, the evidence is strong, we're going to say it's not okay anymore. If H naught is true and we don't reject it, that's a correct decision. Okay, so I'm not going to write a word. I'm just going to put a check mark there. That's okay. So we can be true and not reject it, and we did okay. There's not anything particularly interesting about that. The new medicine's not better. We said it wasn't better. We really didn't gain a whole lot from it. We just made a correct decision. In the court case, the dude was innocent. We didn't send him to jail. That's not really interesting. Okay, H naught is true, but we reject it. That's a bad decision. And that is a type 1 error. Okay, so the highly imaginative names, type 1 error, type 2 error, you got to be able to keep those straight. So what helps me is to remember that I start with truth. I start assuming it's true. So the type 1, the first error, is going to be that the naught is true, and then we made a mistake when we rejected it. On the other hand, if the null is false and we don't reject it, so this is when the new medicine really is better, but we don't think it is, that's an error, and that's a type 2. So another bad decision. In manufacturing, we think that's worse because we have a bad batch of product and we ship it out to our customers because we think it's okay, and we're probably going to lose money and we're going to lose customers. So it's kind of bad. But in jury trials, this one we think of as being the worst. That's when we send the innocent dude to jail and let the guilty dude go free. So the kind of double whammy there. And then the last one, the null is false, which means something really did happen. And we rejected the null and said, oh, yep, we have evidence that something happened. So that's a good thing. Not only is that a good thing, that's what we were after to start with. The whole reason we arrested the dude is because we thought he did something. So we found the guilty dude guilty. That was the whole purpose. So this is where we really want things to happen. And in the world of medical testing, this is where we find the better medicine. We find that this one actually is going to cure cancer. And we found it. Woohoo! Good for us. So this is the powerful one. This is the one we really want. Although this one's good. This one's the best one. So this one actually gets another name. If you take a look at the next slide, there's one that's already made. And you can't read, probably. Nope, it's just hard to read. This one's a top 1, and this one's a type 2. It's just the colors. I copied this straight out of the book resources, and it was just too dark to do very well. Okay, so this one is just that same picture that's putting the truth on the top and the decision on the side. That's all it is. Nothing real fancy there. So we'll move on. Now, so the first thing you have to be able to do on the AP exam is to discuss what type of error you have in context. We'll practice that. We're just not there yet. The second thing you have to do is understand the interrelationship between the probability of one happening and the other one happening, and knowing what you can control and what you can't control. So that gets us to this slide. When H0 is true and we reject it, that's a type 1 error. Okay? And the probability that that happens is alpha, because if we reject, we would only reject alpha % of the time. So we can control this one. If we set our alpha level at 5%, then we're only going to have a 5% chance of making that error, because you're only going to reject 5% of all the possible samples. So if I make alpha lower, then I have a smaller chance of that happening. So if I reduce the alpha level to 2%, then I only have a 2% chance of making that mistake. Okay? The problem with that is if I decrease the probability of making that type of error, it's actually going to increase this one. So they have to kind of balance each other out. When H0 is false and we fail to reject it, we make it type 2. The probability of that is called beta. Okay, so alpha is the first letter of the Greek alphabet, beta is the second letter of the Greek alphabet, type 1 is the first letter, type 2 is the second letter. Those actually, they chose those wisely. Those make sense. Now, in advanced statistics courses, not this one, you actually learn to calculate beta. We don't do that in this class. It's not on the AP exam, so don't worry about it. We never attach a number to that because we don't have the tools to attach a number to that, so don't worry about it. But what we do need to know is if one goes up, the other goes down. So if I make alpha bigger, that means I have a bigger reject zone, then it makes my probability of the other type of error go up. If I make alpha smaller, beta goes up. And it goes back to that picture that was in the reading we did yesterday. You still have a copy of that. That on one side you had green, on the other side you had red, and if you move that line, one gets bigger, the other gets smaller. So you can't fix it all. Next slide. Power. This is a terminology that we have to have some familiarity with. In advanced statistics courses, you learn to calculate power. You can attach a numerical value to it. You don't have to do that for the AP exam. We don't have the tools to do that, so we don't worry about it. But you do need to know generally what it is. When H0 is false and we reject it, so when the dude is guilty and we send him to jail, we did the right thing. If the new medicine is better and we know it is, we did the right thing. And the power of the test is what has happened. We have power when we reject a false null. That's what we're looking for. That's the big deal. And the power of the test is the probability that we correctly do it. So power is measurable. We just don't have to measure it in this class. It is 1 minus beta, but you don't have to calculate beta, which means you don't have to calculate 1 minus beta. But the better chance we have of rejecting a false null, the higher our power gets. The whole purpose of testing is to find that something has changed, something interesting has happened. And to find that something interesting has happened is your power. So if we go back one more time to the decision-making box, next slide, one more time. So let's draw it differently this time. So this time, let's put the truth on the top, the truth, and the decision down the side, just to mix it up a little bit, and split it into 4 pieces. Alright, on the truth side, H0 is true and H naught is false. You could rearrange those if you wanted to, but I'm a creature of habit. I usually do truth before I do false. Just that's my habit. Down the side, we reject H naught, or we fail to reject H naught. Okay. If H naught is true and we reject it, that's bad. So the dude is innocent, we sent him to jail. That is a type 1 error. If we rejected a false null, null is false, to reject it, that's good. That's the dude is guilty, we send him to jail. This isn't just a correct decision, that's power. How much probability do we have of that happening? That's our power. So the higher chances of getting that right, the more power we have. The power of the test increases. H naught is true and we fail to reject, that's a correct decision, but it's not real exciting. You know, it's not really exciting to find out the new medicine's not better. It's not really what we wanted. It's the truth, but it's not what we wanted. But if we have a false null and we fail to reject it, that's still a mistake, and that's the type 2. So we're just going to add one element to the box this time. Power is what we really want out of our test. That's the whole reason we tested to start with, is because we wanted evidence that something was different. How are we doing so far? It's not terribly exciting, but does it make some sense? Okay, this is pretty sophisticated, which is, you know, worst case scenario, you might have to go back and listen to it again. So sorry. It might work. I don't know. We're going to record it, put it on Schoology just in case you want to listen to it again. If you can stand it. At least you can pause and skip parts when you have digital control over my voice. Think happy thoughts. Alright. We're going to wrap this up pretty soon. We are on home stretch, guys. We may have to take a stretch break somewhere along the way, though. I don't know. You guys are looking a little glazed already. Okay. So, understanding the interplay between type 1 error, type 2 error, making one bigger, making the other one smaller, really boils down to this picture. And this is the exact picture that's in the textbook that you guys don't read unless I actually force your hand and like make you like do popcorn reading. So on one, and the thing is, these ideally would be side by side like the pictures that were in the article we read yesterday, but they overlap each other and it's really hard to see what's going on. So one has been sort of, you know, raised up above the other one just so that they don't overlap, but they really could overlap. You could push them down to the same level. So this is a picture of if the P naught is true, which is the proportion that's claimed in the null hypothesis. So if the null is true, this is the graph. There's the true P we're claiming. This line right here, that's your alpha level, okay? If we do, let's say, an upper-tailed test, and we could flip this picture around to a lower-tailed test, it would just be a mirror image. It would be the same reasoning. If we did an upper-tailed test, if we got a sample that landed in the black region, we would reject the null, right? That would be a mistake because the null is true. But if we get a sample that lands down here in the gray area, we would say, no, nothing interesting going on. We'll fail to reject, and that's a correct decision. So gray is a correct decision. And then this upper part, that's your type 1 error area. So if the dude is innocent and we send him to jail, that's that upper dark part. On the other hand, if the null hypothesis is not true, so this is the lower graph, if the null hypothesis is not true, okay, and this is still our alpha level, if we got a sample above that cut line, then we would reject. That's a correct decision. If it's not true and we reject, that's power. Okay, so this is the correct decision. And then down here in this dark space, we would fail to reject the null down there. But if the null is not true, that's a mistake. That's the type 2 error. And if you move that alpha line to the left, the area under type 1 gets bigger and type 2 gets smaller. So you can fix one and mess up the other. If you move that alpha level to the right, then one gets bigger, one gets smaller, and you mess one up and fix the other. At least fix it better than it was before. So since alpha is movable because you get to pick it, you can control somewhat how much error there is. Now, how far apart the P naught that we claim and the true P is? Because if the null is not true, that means the P naught we started with is wrong. How different the true P is from what we claimed, we don't know. We don't know if these two graphs are really far apart or if they're really, really close together. If they're really close together, those get bigger. If they're really far apart, those get smaller. So the more not true the null is, if you can say that, or the farther from the true P the null really is, then the less likelihood you have of getting those errors. I find this to be one of the hardest pictures in the whole book to understand. Anybody else think it's a little bit yet? Okay, I had trouble with this one. Or at least I had great trouble with it at the beginning. So how about we build it from the ground up and see if it makes more sense? We'll try anyway. Okay. Alright, so the upper tail test scenario, building it from the ground up. Okay, so we have a claim. Pretend that's beautiful. The claim is that the null is true. So the true proportion of blah, 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 blah is a number. And that number is this P naught. Okay, so we think of that as the proportion in the null hypothesis. So 40% of blah, 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 blah do this. And we decide that if we set our alpha level at, say, 5%, so we set our alpha level. I'm not going to put a number there because that's changeable. If we put our alpha level there, and then we go look at a sample, if the sample falls to the left, then we would fail to reject. I can't spell. And that would be a correct decision if the sample falls to the left of that line. If the sample falls to the right of that line, that is a rejection of a true null. That's bad. So this is reject, and it's a type 1 error because I rejected a true null. Okay. I'm assuming the null is true. If I make a decision to the left, it's good. Make a decision to the right, it's not good. Okay, let's say that the null is not true. Remember, it's got to be true or false. So what did I start with? Did I say 40% of something is blah, 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 blah. That's what I made up, was 40%, right? I'm going to use a number because it's easier. Let's say that my claim is that 40% of students bring their lunch every day. Okay, I'm just making something up. Let's say the percentage is actually higher. So the real proportion of students who bring their lunch is 60%. Okay, so that means, and I would normally draw them side by side, but it gets kind of hard to read, so I'm going to go down a little bit, but pretend you could scoot it up and they would overlap. Instead of the true P being at 40% as I originally argued, let's say the true P is up here at 60%. So that's the true P, not P that I'm claiming in null hypothesis. And that's the real distribution of all possible samples. So it's higher than what I think it is. Now, here's the thing you got to keep in mind. What I believe, what I'm claiming, is that one. Okay, I'm claiming this. This is what I think is going on, or what I'm assuming is going on. But this is the real truth. Now, which means the real truth being a higher P means my initial H0 was false. My H0 wasn't right. 40% was not the right P. 60% is the right P. I just don't know it. And therein lies the problems. I don't know I was wrong. I don't know the claim is wrong. But if I could secretly in the background know that it's really 60%, my graph is really up here. In that case, remember I'm basing all my decisions on assuming this top one is true. If I get a sample to the left, that left is fail to reject territory because I'm assuming that the top one's true. So anything to the left of this alpha line would be a fail to reject because I'm thinking it's here, even though it's down here. And anything to the right of that is over the alpha line above it, so I would reject. And the fail to reject on this side is wrong. So if I get a sample that falls in this left tail down here, if I get a sample below that alpha and I fail to reject, that's going to be a type 2 error. But if I get a sample to the right, if it's really 60%, and my sample p hat was 62%, and I rejected the null because I thought this was the truth, it means I actually did a correct decision. So this was good. This is where your power lies. This is when the null is wrong and you figure out that it is. You catch it. You find the truth. The lower tail test is the mirror image of that. And in the years I don't look at the lower tail, I usually have people that think everything's bigger. So I'm going to do a real quickie lower tail one on that next slide, and then we really are on the home stretch. The worst is over. If it's a lower tail test, so here's your deal. You start with an assumption that H naught is true, and so P naught. So let's get a different scenario. Let's say that we claim that 70% of students, I don't know, have at least 100 numbers stored in their cell phones. I don't know. I'm just making stuff up. So P naught is 70%. I'm making a claim, okay? So I want to know, maybe somebody challenges it and thinks it's not that high. And so we're looking for a lower tailed test. We're looking for evidence that it's actually lower. Okay, so now we got a lower tailed test. And our alpha level is now on the lower end. So if we're to the left of that alpha, we're going to reject the null. And if we're to the right of that alpha, we're going to fail to reject the null. So if I'm saying 70% of students have at least 100 numbers stored in their cell phone, and I find a p hat of 50%, then I'm probably going to be down here under the alpha and reject the null. Think it's too low. But if I get a number like 68%, then I'm going to be up here and fail to reject. Fail to reject is a correct decision. Rejecting is the wrong decision. Null is true, but I don't think it is. That's a type 1 error. And if I move the alpha to the left, the probability of type 1 gets lower. And if I move it to the right, the probability of type 2 type 1 gets bigger. So that probability, the area under this curve, it is alpha. Okay? So I'm going to keep that line down here. But let's say that, I'm just completely off kilter, and the true proportion of students who have at least 100 numbers stored in their cell phone is only 50% instead of 70%. So the true P is down here, which means my initial claim of H naught being 70% is wrong. It's false. It's actually lower than what I proposed. So the truth is here, what I claim is here. And they could be side by side if it wasn't so ugly. Okay, if I'm to the left of alpha when I collect a sample, because I believe this top part is the truth, if I'm to the left of alpha, I'm going to reject, which means down here is reject zone. So if I get something to the left of alpha, I'm going to reject. Well, since H naught is false here and a rejection is good thing, this is power. And the area under the curve here is called beta. 1 minus beta. Sorry. Power of the test is 1 minus beta. About screwed that up real bad. And then on the other side of alpha, to the right of alpha, if we get a sample that's over there, that sample actually supports our initial claim that 70% of students have 100 numbers stored in their cell phone. So if we got a big sample, we would fail to reject. And that would be a bad call if the null is really false, if it's really lower. So that's a type 2 error. And the probability of that happening is beta. You don't know how big that is. The problem with knowing how big beta is it depends on how far away P actually is from P naught. And we have no idea. If we said the true proportion was 70% and the truth is actually 50%, then we can know a distance. But we'll never really know where P is. So we don't have the tools to calculate beta. There's some nifty something out there that students use to calculate beta at advanced levels. I don't know what it is, but you don't need to, so we're not going to worry about it. But what you do have to know and be able to communicate on AP exam day is, if alpha's here and you move it this way, type 1 just got smaller, alpha got smaller, but beta got bigger. If your alpha level gets moved this way, type 1 error goes up, type 2 error goes down. The only way to make both of those smaller is if both of these curves get taller and skinnier, and the only way that can happen is if you increase your sample size. So more samples, more people, more things to look at is going to make both of those smaller and lessen your chances of both types of error. But you can only lessen them so much. They never really go away because those tails go off to infinity. So in summary, if we reduce type 1 error, we automatically increase type 2. So if we reduce alpha, we increase beta, and vice versa. And vice versa. We can reduce both types by making both curves narrower, and to do that we would have to increase the sample size. It's the only way you can fix them both, and you can only fix them so much because there's a limit to how big your sample size can be. Like, it can't get more than 10% of your population, so you definitely have a limiting factor there. Alright, do you need a stretch break? And then we'll let's do a quick stretch break, and then we'll do... Okay, so highway safety engineers test new road signs, hoping that increased reflectivity will make them more visible to drivers. Volunteers drive through a test course with several of the new and old style signs and rate which signs show up the best. So we're doing sort of an experiment here. In this context, this is a typical AP problem. What would a type 1 error be? And it needs to be in sentence form, and it needs to be in context. But I think it helps to do a little work over in the margin first about what the null would be and what the decision would be. So let's do a little thinking on the side. In this case, what would H not be? The new signs are not better than the old. And I think it's helpful in words if I'm going to have to put it in context. New signs are not better than the old ones. I'm not even going to worry about proportions. I don't have any numbers anyway. Okay, and so a type 1 is when, for this one, H naught is true, and we reject. So for H naught to be true means that the new signs are really not better. That's the truth. So let's start with what's the truth. The new signs are really, so this is reality, this is truth, really not, that's the word really, even though it doesn't look like it, not better than the old ones, but, so truth and then decision. But an error means we made a wrong call, so they're really not better. Therefore, we think the opposite of that, which is that they are. But we think they are better than the old ones. But we think that they are better. Okay? One sentence. Start with truth, end with decision. Are we okay so far? Okay. So this is typical kind of stuff, big idea thinking. In this context, what would a type 2 error be? So in a type 2, H naught is false, but we fail to reject it. So I'm going to kind of do some, I don't know why I can't, I just want to write ject. Fail to ject. I've done that like 5 times. Fail to reject. Alright, so if H naught is false, that means the new signs are better. They really are. So this is about truth. The new signs really are better than the old ones. But we don't think they're better. So just say the opposite. Okay? Context is there. Truth and decision. Context, truth, decision. Alright. Does that work in your head okay? Alright, so task number 1, be able to describe the errors in context. Got that one. Task number 2 is we might have to talk about the interplay between the probabilities of those. So that's this last piece. So part C and part D. In this context, what is meant by the power of the test? So power is when we can reject a false null. So H naught is false. We reject. And it's the probability of that happening. So the probability of having a false H naught and rejecting it. So this is my sort of thinking in the margin to get my thoughts together first. So I'm going to start with it's the probability that. It is apostrophe. It's the probability that we correctly find that the new road signs are better than the old ones. That's what we wanted. Otherwise we wouldn't have bothered with this whole mess. And that says old. I'm struggling with writing on a piece of paper. It's not supposed to be hard, but it's a struggle. Are we okay so far? Alright, so this is kind of a blanket sentence. If you always say, it's the probability that, and you explain what a correct decision is. That's all you got to do. Last but not least, if the hypothesis is tested at the 1% level of significance. What's a level of significance? What? The alpha level. So they're saying alpha equals 0.01, okay, at the 1% level of significance, which means we have a 1% chance of making a type 1 error. Instead of 5%, how will this affect the power? Okay. Well, let's see. So if we have a 1%, oh my goodness, this one's hard to think through. Maybe I need to look at a picture. Let's try a picture. So let me think upper tail test, because we want evidence that the new signs are better, right? So I'm probably looking at upper tail test. So if I started at alpha equals 0.05, so I'm making notes up here before I've read the whole problem. That's not always the smartest thing. So I would have rejected the null with 5% of the possible samples. Okay, power is about rejecting a null, right? Yes, Ms. Rose, it is. Thank you for playing. It is. It's about rejecting the null. If I take that to 1%, so if I go down to 1%, am I more likely to reject or less likely to reject? Less, yeah. If we lower alpha, so we go from here to here, lower alpha equals less likely to reject. If we're less likely to reject, and power is about rejecting a null, then we had to have just decreased our power. So, power decreases. Because we're less likely to reject. And power is about rejecting. Alright. How we doing? It's a lot of information, okay? But we got 2 days to process and do practice with it. So I'm going to click on stop. And